through and attempting to solve these kind of questions, we do have to do some kind of simple things first, okay? Simple reporting. What do we see? What is in the question that allows me to interpret and start this process? If you don't do that reporting stage of what's there, it's very hard to do the analysis stage of now how do those pieces fit together, okay? Or technically the synthesis of then putting those pieces together. Okay, so what we would have to go through and do is start breaking it down and saying, well, what do I see? Okay? In a conversation that I had with one of your colleagues, the first thing that they saw was HCl aqueous. Okay. Cool. Is that an important thing to report? Okay. Is HCl aqueous given as a standalone thing? Or is it part of a larger statement within the expression or within the question? So for instance, if I erased everything else, does that hold the same meaning right there? Does that hold the exact same meaning as this? Do those two systems hold the same meaning? No. Okay. So what does that mean about the HCl aqueous then? What does that mean about the HCl aqueous? Not that you can ignore it. So the question was, can the HCl aqueous stand on its own? Theoretically, that'll come back here in a second. Okay. If it can stand on its own, what can I do with everything around it? Ignore it. Okay. Which would mean the meaning of HCl aqueous on its own. So if I just look at that, that right there has the exact same meaning.
You're not ready.
Okay. Might help if I fix that. So let's see. Why not? Is it working? Okay, we're working. Does HCl aqueous, that right there, mean the exact same thing as this? Okay. And I'm hearing a significant amount of people saying no. I haven't heard anybody say yes. Okay. Why are you saying no? What is the rest of the information included around the HCl? What does that stuff mean? What does the plus sign mean?
It's reacting with something else.
It's reacting with. This is a mathematical expression saying that I'm taking aluminum solid and I'm mixing it with HCl. What does that mean? I have HCl. Are those meanings too different? Yes. Okay. So it is important to acknowledge that HCl aqueous is present, and that is valuable. Okay. But is that information part of a larger piece? Yes. Okay. Which means I can go through and report that information. I can write down HCl aqueous, but I have to remember that that HCl aqueous is part of a larger piece. It's part of this entire thing. So that might be a useful piece of information to write down. Okay, so that is my reporting out. So when most people went through and started to solve this, I saw a lot of people writing down that chemical equation. That was phenomenal. Why were you doing that? Because you've decided that that's an important piece of information. Okay? Another suggestion is, well, I need to balance it. Okay? So let's work with that. So everybody agree the equation is still present? Mm-hmm. Yeah, okay. Do I need to write down the equation? It's still there. Why are you now not writing down the equation?
It has
pertain to the
nothing to
question.
do with.
It has nothing to pertain to the question. Okay? So your reflex of writing down the equation is a decent reflex, but unfortunately at this stage, it's just a reflex. Like, I need to balance an equation. Do you? What color is Mike's shirt? Do you need to balance that equation to figure out the color of my shirt? No. Admittedly, it's one of those weird salmon-y, pinky colors, and it might be difficult to label which one it is. Okay? But that's beside the point. Okay? So what you need to think about is, why am I writing that information down? Okay? It is a choice to write that down. Okay? To kind of piggyback off of another class, in an English class, you're supposed to write an essay. And you're supposed to write sentences about what? A topic. What topic?
Whatever topic was assigned to you.
Okay? If you're only supposed to write sentences about a single topic that was assigned to you, what happens to every single paper that gets turned in? It's the exact same. Is every single paper that's turned in an English class the same? No. Why?
Because you're allowed to put your opinion in it.
You're allowed to put perhaps your opinion, and your opinion is going to influence how you write that, but you're going to see that topic in a different light from somebody else, so you're going to approach it slightly differently. You're going to make different choices about what is important to address than somebody else. Right? The same thing is happening in science. Right? Believe it or not. However, science is a little bit more regimented, and so we start to lose some of that flexibility. Okay? Or we decide it's way too hard to teach people how to think, so I'm going to go through and tell you an equation for how to solve. That way I don't have to teach you anything. I can just say, here's an equation, memorize the equation, plug stuff into it. Okay? Which is phenomenal if you were a robot. Okay? I guarantee you this computer can do it faster than you. Okay? You're out of a job fast. You need to know why you're putting those pieces of information together. Kind of make sense? Okay. So, while writing down the equation may be useful and will come in handy, the reason you're writing it down is because you just have this gut response, well, this is a chemistry class, I need to write that down. Okay? I want it to be a little bit more intentional. I need to write it down for a particular reason. How would I know what that reason is?
Do you know you're doing conversions?
How do I know I'm doing conversions?
Going from one substance and measurement to another substance and measurement.
What is the other piece of reporting that I have to do from this? I want to find how many liters of hydrogen are produced in the reaction with 0.165 grams of aluminum. Okay. I've now done some reporting of basic facts to acknowledge what things are there, and now I can start my process. I would argue that what I should start writing down is not the chemical equation, because who knows, this could be Mike's pink shirt. Okay. I don't want to write down the chemical equation. That's not relevant for me solving the question. Okay. What is the question I'm being asked to solve? The liters of hydrogen. So we're again starting with that goal. What's my end goal? Why am I doing this? Okay. What am I given to start with? Grams of aluminum metal. Okay. And I'm given a numerical value that I can tie to that. Now that I've reported this information down, I'm trying to make those two things equal to each other. Do those two things equal each other? Is grams the same thing as liters? No. So what do I need to do?
Change the
I need to convert them. Is aluminum the same thing as hydrogen? No. So what do I need to do?
change the substance.
I need to convert them. I have to be able to come up with the conversion factors to do that. Okay? What conversion factors I choose are like choosing the words that I put together in a sentence. Okay? And I have to be very intentional about those decisions. If I don't make the right decision, okay, my sentence makes none. Right? I think I actually got that. Okay, so we have to try and think about that process. Okay? Does that mean all sentences have to be the same? No, there can be variation. So when we look at grams aluminum, liters of hydrogen, we now have to decide, what do I want to try to convert? Okay? I would make the argument the substance is arguably the most important thing to deal with. Okay? Because I'm in a chemistry class. I'm trying to make something. So I want to think about how I could convert that substance. Well, how do I convert that substance? No. Moles doesn't convert substances. What converts substances? A balanced chemical equation. So that reflex of writing down the chemical equation now has a reason, because I need that to figure out how to convert the substances. So now I can go through and balance the equation. Does that make sense? So don't just immediately start copying things if you don't have an intent behind it. Right? And if your intent is, well, I have no idea how to solve this, I need to put as much stuff down here as possible so that Mike pretends to give me points, that's fine. But that is an intent. Right? That intent has to be there. Don't just start writing stuff down because you're wasting your time. Kind of make sense? Okay. So, to the argument, substance needs to convert, we should balance an equation. This equation was not an easy one to balance because it constantly changes on you. So we could go back through, and I'm going to attempt to balance it quickly. 2, 3. Did I do that right? Cool. Okay. What is the measurement unit associated with the substance? So the chemical equation gives me the substance conversion, but what is the measurement unit tied to it? Mole. Now we can say moles. Moles on its own wasn't a valid thing until we had a reason for why we could do it. Okay, so in that, I'm trying to do a conversion to get aluminum converted into hydrogen gas. And I know that that conversion factor, that substance conversion, comes from the balanced chemical equation. And I know furthermore that the balanced chemical equation gives me moles as my measurement unit. Come on, moles. What are the numbers associated with those units? 2 aluminum is 3 hydrogen. I was just testing to see if you were paying attention. Oh my gosh, that's
beautiful. What did you get that? It's gorgeous.
not that it's much better, but okay. What is the problem with using this conversion factor early on?
Cancel grams.
Did I cancel grams?
Not yet.
No, I haven't canceled any units. I've acknowledged the importance of setting up that I need to do this conversion factor. It has to happen, but I haven't simplified my expression. That doesn't make it wrong. If anything, I have a better intent. I know what I'm trying to do. And I know the only place to convert those substances comes through the chemical equation, and I know the unit that's for that has to be moles. Okay? Which means I need another conversion factor. Okay? And now what conversion factor do I want to bring in? Okay? Just, you didn't like grams, so what should I do? Let's deal with grams. Okay? I don't want grams in my expression. Okay, well, what could I convert the grams to? Okay? I could convert them to moles. I could convert them to AMUs. I could convert them to kilograms, micrograms, pounds. Which of those conversion factors, which of those make the most sense to incorporate into my expression? Why moles?
Because moles of aluminum
Because I don't know that that's going to make any sense.
Because you can't do substance and measurement conversions at the same time.
Well, you guys just told me moles, so I assumed the substance wasn't important.
You know, moles.
Moles of aluminum.
You mean I can't go moles of hydrogen?
No.
Why not?
Because you can't change the unit and the measure at the same conversion.
I cannot convert the measurement and the substance at the same time, which means this is an invalid conversion. So when we're talking about our units and our conversions, we have to be very, very, very careful to make sure that we always tie the measurement and the substance every single time. Right? Which means I'm not going to moles of hydrogen, I'm going to moles of aluminum. Why is this conversion factor now a pretty cool conversion factor? I can get rid of the grams of aluminum, right?
No. Moles of aluminum.
And I can get rid of moles of aluminum. It does two things in one fell swoop. That's pretty awesome. Where do I find that magical conversion factor that does all of that work for me? That comes from the periodic table. Okay? That comes from a mass, because I'm using units of grams. Okay, so where's the mass on the periodic table for aluminum? Where's aluminum? I see two numbers, 13 and I'm rounding 27. Why 27? That's the weight, and weight is a measurement of mass. Okay? So I could go through, again, I'm horrible, I apologize, I'm rounding, just deal with it, and 1 mole. Okay? Does this now solve my expression? I canceled a whole bunch of stuff. I'm even in units of hydrogen. But I'm still not fully across into the proper unit, or the measurement unit, so I would need to go through and recognize that moles of hydrogen needs to change to liters of hydrogen.
Which we can't do that
Okay. Is there a conversion factor that allows me to relate moles and liters?
Yes.
Yes, there are two. What are those two?
1 mole is 22.4 liters for gas.
1 mole is 22.4 liters, and what's the other one that relates moles and liters? Molarity. Okay, 22.4 liters is equal 1 mole, sorry, okay, is true for
Gas.
STP and gases. Molarity is true for
Everything else. Oh, solution.
solutions. It has to be a solution. Right now, the only solution that we have to work with is what phase? Aqueous. Right? Is the hydrogen aqueous? How do we know what the phase is on hydrogen?
Because it's stated.
So, number one, it's stated. It's in the equation that you were asked to solve for. Number two, you're responsible for knowing that. Why are you responsible for knowing that hydrogen is a gas?
No, because Mike told
That's
me to remember.
kind of a painful one to say, common sense. That's kind of mean. Okay, another option is blame Mike. Mike said to do it. Okay, another option is it's literally already on the periodic table. Right?
Oh, it's really blue.
Hydrogen is red. Not all elements are. Why is it red? Red is a gas. It's on the periodic table. Right? So there's a lot of information coded in different places. You have to recognize how to decode it. So hydrogen is a gas. So what does that mean about the conversion factor of 22.4 liters and 1 mole? That it potentially works. Why does it potentially work? It has to be at STP. Does the question clearly state STP? No. Unfortunately, what are they making the assumption of? That it's at STP. If you see this on an exam, you should raise your hand, okay, and ask. There's one case where you don't have to raise your hand and ask. Look at your answer choices. If one of your answer choices says impossible to solve, you should immediately raise your hand, because this question is impossible to solve, okay, until I know it's STP. Okay? It's a sneaky, nasty, backhanded trick that I do. Okay? It should explicitly state STP. If it doesn't, the question becomes impossible to solve. When do you not need to raise your hand? When it says at STP or
Celsius.
273, 1 atmosphere, yep, keep, or
0 Kelvin.
the concept of STP in any way, shape, or form is not listed in the question. How do you know not to ask? And again, remember, this is a multiple choice question.
There's no choice says cannot be solved.
None of your answer choices say cannot be solved. Okay, which means you can solve it, which means it's implied that it's at STP. Should it ever be implied?
No.
Hell no. Okay? So if in this class you're like, I need to know, Mike, like, are you trying to be a jerk? Okay? What you might get from me is, sorry, all the information you need is there. That's probably code for look at your answer choices and one says not solvable. Okay? And another choice, or it says STP somewhere up there. Make sense? Okay? In future classes, you may need to raise your hand, depending on how detail-oriented that instructor is. Does that make sense? Okay, so it is at STP, which means
You can solve it and you can use the conversion.
22.4 liters is 1 mole. And what happens? Moles of hydrogen cancels. We'd end with liters of hydrogen. We can now punch numbers into our calculator. Gently, you don't want to break the calculator. Make sense? Like one person laughed, that's okay. So we good? Okay. So you have to know the reason behind why you're putting those things there. It's all about the intent. Okay?
On the show your work stuff, are you going to be looking for like where we like how you put BCE and periodic table, all that?
Good question. I'm not expecting you to write, and I should actually finish that out. I'm not expecting you to go through and write underneath these things where you found that information. Okay? So the first one, we found that conversion factor from the balanced chemical equation, BCE. The second one was from the periodic table, PT. The last one was, okay. Yeah, I always mess up Brain and Brian. Okay. So from your brain, you have to have, you laugh at me, you start writing Brain a bunch, you'll start screwing it up too. Okay.
Especially if you have a friend named Brian.
Yeah, it happens all the time. And if they're smarter than you, it gets even worse. Okay? So we have to be able to acknowledge those. So I've been trying to show you where those conversion factors come from and always writing that information in. That is not part of the required work. However, if you've gone through and looked at the practice exam, okay, you will find that I will ask specific questions. Where would you find the conversion factor that relates mass to moles? Okay. I've got questions that will specifically ask where would you find that information. Okay. I don't expect it to show up in your work. I do, and I'm asking those questions in the multiple choice to be like, dude, you need this somewhere else. Here it is. Okay. Trying to help out. Make sense? Okay. We cool? Let's be done with it. Okay. Y units, so this is just a quick thing. I skipped over it earlier, and just because I was already in a roll in gases and angry and stuff. But okay, conversions. We could go through with, and a lot of people have seen things like this in particularly high school classes. Right? I can solve for the moles by taking the mass and dividing by the molar mass. Okay, that's true. That's an algorithm that allows you to solve one question. You can even arrange it into weird, goofy triangles. And cool, you want to do that. That allows you to solve 2 questions, 3 questions. Right? Dimensional analysis allows you to solve every single one of these without an equation. I don't have to memorize anything. I just have to know the process and the intent behind it. These things now become more complicated to memorize those expressions. The dimensional analysis, which isn't my method, by the way, it's just how you do unit conversions. Okay? allows you to solve more questions. You do have to know where to find this information. Even if you did the standard method with here's an equation, this is how you solve it, you still have to know where to find that information. Right? So you're memorizing more stuff. I personally have a crappy brain and I try to avoid putting anything in there. Right? So it's nice and empty. Shine light. Sometimes it's magnified. Okay? So that's the point of dimensional analysis. Avoid that memory. So atmospheric pressure. So pressure is one of the things that we said could happen. So there's a force that gases push on their system, or whatever their container is. That force we've called gas pressure. Okay? Pressure is something that we can observe. There is pressure being exerted on us right now. How do we know that?
Because we aren't exploding.
On the ground isn't gas pressure. On the ground is gravity. Okay, there was another suggestion. What happens if we got rid of the air pressure?
Be in a vacuum.
We'd be in a vacuum. So nothing is pushing on your skin to keep your skin here. So what does your skin do? Okay, we'd all be these big nasty blobs if our skin was somehow able to stay intact. Okay, that would not be particularly pleasant, right? But it could be fun, like those bouncing things. Yeah. Okay. So the atmospheric pressure, it's there. It's there, and we can observe it. And we can notice that when we change altitude on our planet, that we also see the pressure change. Okay? And we could feel that pressure change. Right? If you go to higher altitudes, what's that? Your ear pops. Okay? What happens if you go, how many people have scuba dived? Okay? I've never scuba dived, so I don't really know. But you could go really, really low in the water, right? And you start to feel like compressed, maybe?
Yeah, well,
Your ears feel like
not
they're
really.
gonna burst.
You have to equalize your ears over and your nose, or else your nose just explodes.
So we feel pressure when we go down, and we have to equalize it so that we don't explode. Yeah, we are feeling pressure, yes. Okay? What happens when we go down really, really low, and then you say, I want to take another breath, but from fresh air.
Your lungs.
So I'm just going to skyrocket to the surface.
You get
Your lungs
air bubbles
expand
in your
and blow up.
bloodstream.
Your lungs expand and blow up. Okay? So when we change altitudes, we change those pressures. Okay? And going underwater is a whole nother pressure system, because now it's water being the pressure, okay, as opposed to gas. Okay? So we can measure this. Okay? And the way we potentially measured this was because some goofball was playing around with a container of liquid in a tube of liquid, okay, with a closed end at one part. Filled the tube up with liquid and then put it in the container. It was like, oh, because of gravity, all the liquid should fall out. Did all the liquid fall out? No, some of it stayed in the tube. Okay? And then they took that same tube and moved it to a different altitude, and what happened? Some more liquid fell out. Or some more liquid went back in. Okay? And they're like, well, that's just kind of weird. That's some hocus pocus stuff. I'm going to stop moving it. So I stop moving it and just leave it alone, and I just watch it. Okay? And over the course of weeks, days, or months, the liquid starts moving up and down a whole bunch. What the? This is some scary stuff. What is causing that liquid to move up and down? Atmospheric pressure. Right? That stuff that I can't see that's keeping me together is causing the liquid in that tube to dance up and down. Okay? But it's in a tube. How is the gas outside the tube touching the liquid in the tube? I mean, the tube protects it. How is it affecting that liquid inside the tube?
It's pushing the water inside the container, which is forcing the liquid into the.
It's not touching the liquid in the tube. It's touching the liquid underneath the tube. And if I increase the downward force on the liquid outside the tube, that liquid has to go somewhere. Where does it go? Up into the tube. If I start removing that downward force, what happens?
The liquid drains out.
Then the liquid over here moves up, but as it moves up, something has to replace it. This tube liquid moves down. Okay? So atmospheric pressure is holding the liquid in the tube. Okay? When we noticed that that liquid was moving up and down, we said altitude changed it. But when we just left it on the counter, there was no altitude change. Why is liquid moving up and down? Admittedly, it's slow, but I can see it all of a sudden move one direction. And then it starts to rain. Ooh, I'm going to make the liquid move down and it rains. Right? No, that didn't work. Why is that causing the liquid to change? Atmospheric changes in atmospheric pressure relate to weather patterns. The birth of meteorology. This magic hocus pocus liquid moving around tells me it rains. Okay? So we can use that to help predict things. Okay? One of the other things that we have to worry about, though, is that the liquid in that tube is very often mercury. Okay? Well, isn't mercury a metal?
Yes.
Yes. How do you know mercury is a metal? Periodic table, and what about the periodic table? Because hydrogen isn't a metal. It's on the left side of the periodic table. Hydrogen was a bad example because it's just weird. Helium isn't a metal. Right? It's on the right-hand side of that staircase. Mercury is left-hand side, so it's a metal. Aren't metals solid?
Can that be a liquid metal?
Most metals are solid. Mercury happens to be a liquid metal. Have you ever heard of mercury referred to as quicksilver? Why is it quicksilver? I'm totally making this up, by the way. Because it moves. It's quicker than silver, right? I could very easily be right. I don't know. I don't know the origin of that, but it works. Right? So mercury is a liquid. And we use mercury in these tubes. We don't use something like water. Why not?
Would it not work the same with water?
Good. It doesn't work the same. It's a nice, easy answer. It doesn't work. That's why we don't use it. I like it. It's not good enough.
Are other liquids too thin?
Because water has height.
It's not necessarily thin.
So is water soluble? Or it would be soluble in water?
We don't want to dig into that one too far. If I take liquid mercury and I put it on the counter, what happens to it?
It stays clumped up.
It stays there. What happens if I take liquid water and I put it on the counter?
Spreads out.
Oh, so liquid.
It spreads out and eventually
Evaporate.
it evaporates. It turns into the gas phase. So if I have this container that has to be open to the atmosphere, what happens if I put water in there? The water turns into a gas. Then where does the gas go? Away. It fills the container that holds it. What's the container that holds it if this is open to the atmosphere? The planet. So all of that water now fills the entire volume of the planet, which then means there's less water down here. If there's less water, what happens? It needs to get replaced by this water coming down. So if I use water instead of mercury, the water evaporates and is no longer present. Mercury, interestingly enough, doesn't evaporate, okay, as easily. Okay? So that's interesting. We're saying water in its liquid state exists as a gas. Some of it exists as a gas. Mercury, however, does not. Okay? How do I measure the force of a gas? Pressure, there we go. Okay? It is that pressure. And we're talking about the pressure of that liquid. Okay? If the pressure of the liquid in the gas state is really, really high, well then I could reference the liquid as having a high pressure. But liquids aren't gases. How can I reference the pressure then? Because the pressure is referencing the gas. So I'm talking very specifically about the pressure that's coming from a liquid, not just all gas pressures. I need a new term. Ta-da! We would call it the vapor pressure. Certain substances transfer to the gas phase quicker than other substances. Okay? That becomes important for us. Okay? Something about those molecules causes them to jump to the gas phase at lower energies than others. Okay? So there's some kind of attractive force there. That attractive force we will talk about in the next unit. Okay? It's cool, fun stuff, in my opinion. Okay? So vapor pressure is how much of our liquid becomes a gas, like right away. Okay? Not at the boiling point. Because at the boiling point, how much of our liquid becomes a gas? All of it. Okay? That's now a gas, not the vapor pressure. Vapor pressure is specifically referring to, here's a liquid, how much of it is in the gas state. Okay? Kind of makes sense? So, what would happen to the vapor pressure as we increase temperature? Why would it increase? And don't tell me because you read it off the slide. That doesn't count.
Because as the temperature increases, the gas expands, and so that creates more pressure. So, well, becomes more active, more excited.
The liquid molecules become more excited. The more excited they become, the more likely they become a gas. So as we increase temperature, we're starting to get closer to it all becoming a gas. So more of it comes out as a gas stage. So when you increase temperature, you get a higher vapor pressure. Okay, so there's a direct relationship there. Okay, and we're going to double back real quickly. Back to this thing. The height of that tube, or the liquid in that tube, now gives me an idea of atmospheric pressure. Right? So I can say, well, it's about 3/4 of the way up the pipe. When it hits halfway up the pipe, it's going to rain. That would work. Okay? How precise is that measurement?
Not very.
Not very. How can I make it more precise?
Getting the exact measurements.
Giving it a numerical.
Okay, a numerical number. So it's at 5, and when it gets to 2.5, I am 60, 76, 76. I am 76. What?
Well, no, because you didn't give a unit. Yeah.
Oh, interesting. The numerical value isn't useful. What would we need to do? Give it a unit. 76 inch. Yeah. 72 is 6 feet. So, yeah, there we go. I was right. 76. Okay. So 76. You're not 76. You look younger than that. Thank you. Okay. I'm not 76. Okay. But 76 inches, it makes sense. We need units to tie to that. So what units could I use to measure the height of that tube? Or rather, the length of the liquid within that tube? What units do we use to measure length? Inches. Good answer because it says inches. Phenomenal. Okay? What else could we use to measure it? Millimeters. Centimeters. Miles. Any measurement unit we could use. Why do we pick inches and millimeters? The tube isn't that big. It makes more sense to go in inches than millimeters, right? Or even for that matter, centimeters. Right? When we measured this for atmospheric pressure, okay, at sea level, okay, we noted that it was roughly 29.9 inches of mercury. Right? Do we have to say inches of mercury?
Yes.
Yes. Why? What happens if I change the substance?
It's not going to be 29.
The height changes. So I have to specify the substance in the tube, okay, even though I'm measuring a distance. Okay? Because inches is imperial, or what, I don't know, one of those weird unit systems, we switch it up and sometimes you'll hear reference to millimeters mercury, okay, or centimeters mercury. Right? Which means we now have a new measurement system for assigning pressure, and we have new units, and if we have different units, what do we then have to do? Yay! We get to convert between those unit systems. Okay? Thankfully, pressure wasn't this like inherently obvious thing to everybody in the world, and we only have a few measurement systems, right? Okay? You didn't consider like the pressure inside a tank being different from the pressure inside your car tires versus atmospheric pressure. Like when you think about the pressure inside your tires, you totally think inches mercury, right?
PSI.
You think what?
PSI.
PSI, pounds per square inch. What are we saying there? Pounds, how much force is being exerted per square inch? Guess what that pounds per square inch is? A pressure unit. Okay? Which means, because pressure is actually something that is insanely common, there's a crap ton of pressure units that we could convert between. Right? It's phenomenal and fun and exciting if you love unit conversions. How many of you love unit conversions?
That's what KPA stands for.
Don't worry about it. We don't need to worry about converting the numerics between these. Okay? The one you need to remember, 1 atmosphere. Why 1 atmosphere?
Standard.
That is our standard pressure, but 29.9 inches of mercury is also standard pressure. So is 76 centimeters of mercury, so is 760 millimeters, so is 760 torr, so is 14.7 psi, so is 101 kilopascals. Why are we memorizing 1 atmosphere for standard pressure?
Because it's small, it's easy.
It's an easy number. So when you're asked for standard pressure, you can say 1 atmosphere. If you're asked for PSI, standard pressure, I did not have to worry about that in my class. If I have to move into 151, then I will worry about it then. Okay? All you need to know is 1 atmosphere. That's what I want. Okay? If you do textbook questions, they will have you do conversions. These are your conversion factors off of this table. Okay? If we look at that first line right here, what this is saying is 1 atmosphere equals 29.9 inches of mercury. You could now set up a conversion expression from that equality. Make sense? Good. We're moving on. So, variables that affect gas pressure. What things might you think affect the force that a gas pushes?
Temperature.
Temperature. If we heat things up, what happens?
Becomes more active.
It becomes more active. The more active it becomes, the higher the pressure, because it's hitting the walls with more energy. So what we could go through and do, if we were so inclined, is to say that pressure, when increased, or temperature when increased, increases the pressure. So those would be known as directly related. Okay? Somebody went, oh, that's kind of neat. I wonder if it is a linear relationship or a 1-for-1. If I double the temperature, what happens to the pressure? Does it also double? Or does it go up by 3/4? It wouldn't go up by 3/4. 4/3. Okay? Does it go up by 4 times? What is that relationship? So someone went through and noted that when we look at pressure, we see that it is directly related to temperature through some constant relationship. So that means if I double temperature, pressure doubles, because this thing stays constant. So that's kind of neat. It's a 1-for-1 relationship. Okay. What else could we look at? Volume. How does volume relate to pressure?
Bigger the space, the less pressure.
Okay. More space, less pressure. Really? Right. Let's look at it this way. I put you in a tiny little box. Do you feel a lot of pressure? Okay. But if I make that box a lot bigger, you feel a little less pressure. Right? Same thing's happening with gases. Right? So as we increase the volume, pressure goes down, decreases. So these are not directly related, these are inversely related. Okay? Yeah, direct was a horrible term. Inversely related. All right, what else would affect pressure?
More gas.
Okay? How about the number of particles that are present? God, number of particles. Geez, this is a horrible thing to have to write out. It's a lot of work. How often am I going to deal with really small numbers of particles? I'm probably not going to deal with it a lot. I'm probably going to be dealing with massive amounts of particles. So massive that I decide to invent a new unit to represent that massive amount. What is that new unit that I invent? Ted. Moles. Okay? Notice for volume, what did I pick as the symbol representing volume?
First letter.
The first letter. Right? So we could do the same thing for moles. What is the first letter for moles? M. What's the problem with M?
And it's already taken.
That's already taken in a bunch of different places. Blame physics. They got mass, right? So we can't use M. Okay. So what term do we pick? We pick N. Why N? N comes after M. Duh. It's from the number of particles. All right, that's why we're picking N. So it's not a duh, by the way, for those of you who are like, man, that was rude. No, it wasn't obvious. Okay. Those of you who are like, that was obvious to me. I wrote number of particles, so give me a little bit of credit. Okay. And number two, I probably didn't recognize that the number of particles was N in moles. For 10 years of chemistry. Just for the record. So N. What happens is I increase the number of particles. What happens to the pressure? Why would the pressure increase? It's like filling the room with a bunch of people. Okay? We start to run into a little bit of problems with that analogy, but it's the same idea. Okay? It increases pressure. Okay? So if we look at this, pressure is related to the number of particles, it's related to the volume, it's related to the temperature. Different people at different times through our history went through and noted the relationship between each of these and noted that there was a direct, or not a direct, but a constant that allowed us to see the relationship between these. So all of these ended up with kind of direct relationships. Okay? They may have been inversely related or directly related, but they were all connected. So somebody really smart and said, well, if these are all connected, why am I looking at it as a whole bunch of different things? Okay? So these are some of the smart people. Boyle, Charles, Gay-Lussac. So they said all these different things. Cool, you put all that together. And someone said, well, if I take all of that information and I just kind of fit it together like a little jigsaw, okay, I get an interesting expression. I get a single expression that relates pressure, volume, the number of particles, and temperature to R.
That's your constant.
What is that R? I used that weird little alpha symbol before. I don't know why I did, it just did. Okay. It's a constant. So someone organized all these things around, and they noted that, sorry, other button. They noted that when I take an individual gas, I monitor its pressure, its volume, the number of particles, and the temperature, and I put them into this expression, regardless of the gas, it equals the same thing. If I increase the pressure, okay, so I try to just change the pressure, ends up not working. If I try to just change the pressure, or change the pressure, one of those other terms also changes. That change counteracts so that the end result is still always a single constant. So every condition I run, I get the same R value. That R value, that constant, is 0.0821 atmospheres times liters per mole times Kelvin. What units do we say were important for pressure? Atmospheres. Where's pressure in my solving for R? In the numerator. Where's atmosphere? Numerator. What's my unit for volume? Liters. Where's liters? Numerator? Numerator. What was my unit for N, number of particles? Moles. That's located where? Denominator? Denominator. Temperature? Kelvin. Here's an interesting shift. We shift to kelvins. Why would we shift to kelvins when looking at gases as opposed to, say, degrees Celsius or degrees Fahrenheit?
Because with Kelvin absolute.
Kelvin is the science of why do I care?
Because it's a set number.
No.
You can say no about absolute zero.
Absolute zero becomes important. Okay. What makes Kelvin different than Celsius and Fahrenheit?
0 is the lowest point.
0 is the lowest one kind of helps. There's another one. What do Celsius and Fahrenheit have in common that Kelvin does not?
Degrees.
They're both as opposed to somebody mumbled it. Negative. Degrees Celsius and Kelvin both go negative. If I plug a negative value in for temperature, what happens to R?
Right to negative.
Ooh, it becomes negative. Would that be constant anymore? No, now it's changed. Okay? So when we go through to solve for R, we have to be in units of Kelvin because Kelvin does not go negative. It simplifies our expression so that we can solve for a constant R. If we don't use Kelvins, everything goes haywire and we can't find those relationships as easily. Okay? So now the next question is, what can we do with R? Okay, well, let's take a look at a gas. Okay? I take a gas, I monitor its pressure. Okay? That gas starts with a certain number of particles, starts at a certain temperature, and starts with a certain volume. Okay? What could I do? Well, actually, let's not do the gas yet. What can I do with this expression? Okay, well, if I know R, and I know moles, and I know temperature, and I know volume, what could I solve for? Pressure. Okay? What if I don't know moles? You're like, well, if you don't know moles, then how would you... Yeah, exactly right. I want to know how many moles. How could I solve for the moles? Okay. We can just rearrange this expression to solve for the missing term. Okay. So those of you saying, well, this looks like you're telling me to memorize an equation. Yes. So for all of you are like, just tell me an equation. Ta-da! Memorize that equation. Okay. I would argue that equation isn't very easy to memorize. So what I have memorized was this. Why is this expression easier to memorize? There's no fractions. Okay? We've just shifted everything around so it's a nice linear expression. Okay? So depending on what I'm being asked to solve for, all I got to do is get it by itself and shuttle everything over to the other side. Right? And as long as I'm not changing too many things at once, I can solve that relatively quickly. Okay? The other reason why, okay, is that for whatever reason, back in high school, a teacher said, well, it's just PIVNERT. Yeah, PIVNERT. P-V-N-R-T, PIVNERT. So you might hear chemists refer to PIVNERT. That's what they're talking about. Okay? The ideal gas expression.
Do we have to memorize
The 0.0821, you might need to check me, but I'm pretty sure I gave it to you on the test. Okay? Largely because I forgot it. It's really, really important. Okay? It is an important constant to memorize. It's going to be important for gases. Okay? So we could then use PIVNERT to show all these fancy relationships, and we could solve for questions based off of this. Okay? So we could theoretically calculate everything out. There's our PIVNERT. We can look at conditions under a gas at conditions A, and we could look at a gas under conditions B. Okay? The fun thing about those two conditions is that I know that the R for conditions A and the R for conditions B are the same. So I can set those two expressions equal to each other and go through and potentially solve them. Okay? So what do I mean? The volume of a container is doubled. Assume the temperature in moles are not changed. What happens to the pressure? Okay. So there's a variety of ways you can go through and do this. Some of them go back to Boyles or Charles or whatever, where they came up with their relationships. We could also use these expressions to help us out. Okay. So what do they say happens to the temperature? So temperature under conditions A equals
temperature at condition B. Moles under condition A equals moles of condition B. Okay? The volume of the container is doubled, okay? Which means the volume for condition B is 2 times volumes of condition A. All right, what can I now go back and do? Well, remember I said these two expressions were equal to each other, so here's a massive equal sign. Okay. I wanted to know what happened to the pressure. Okay, so I'm solving for pressure B. How did it change? Okay, well, what do I know about volume A?
Double that.
I just know it's volume A. That's it. So I don't know any numerical value. What do I know about moles of A? So what is the moles of A? Moles of B. So what can I do up here? I don't want to cancel quite yet because I want to make sure it's obvious that I can cancel it.
Multiply both sides by
Could just be one.
Moles of A becomes
moles of B.
moles of B. What is temperature A?
Temperature B.
Temperature B. What happens to my expression? These parts are equal, which means those, for those of you that were jumping straight to it, cancel. And I would get pressure A. I know A is an upside down V. Times volume A equals pressure B, volume B. Well, what is volume B? Yeah? Okay, what was I solving for? Pressure B. So what can I do? What is pressure B? Times volume A? Volume A cancels because they're the same. What is pressure B? 1/2 of pressure A. Those of you going, I could have just done that with those expressions that you talked about earlier. Yes, you can. Okay? I'm not saying that you can't do that, but what I'm trying to show is that PV equals nRT allows you to do that. You don't have to memorize each of those individual relationships because the relationships are right there for you. Okay? So we can now see what happens to those pressures, right? Or those volumes. So by setting those two systems equal to each other, identifying given information. Okay? So temperature A equals temperature B. What did I do there? How was I allowed to set them equal to each other? I reported information from the question. I just reported it in a mathematical expression that would allow me to then manipulate it within the mathematics. Make sense? Okay? So, I keep pushing the wrong button. So here's the one. Moles of neon gas occupy 2.43 liters at STP. Okay, so we're going to do a little bit of a race here. Okay, so you guys, I'll give you a little bit of a head start. Go ahead and swing at this, start getting this solved. Okay, figure out what you want to get, all that kind of fun stuff. And because it is a race, you should probably ignore what I'm about to write. Because I'm pretty sure you can do it faster. Okay? That's what I want. Yeah, that's what I want. I said don't look at my work, for those of you saying, oh my God. Anybody solve it yet?
Yes.
Damn it, I lost. Okay, I need someone to help me out here. Okay. For those of you that did solve it, did you do all this work? It's not fair. So what'd you say? Did you say something along the line of I'm trying to solve for moles of neon gas? And I started with 2.34 liters of neon gas. And I was trying to do the conversion factor to get rid of liters of neon gas, and I wanted moles of neon gas. Oh, and this was a gas. Okay, so gas. And it actually even says at STP, which then means 22.4 liters is 1 mole. That was pretty fast. That was a little bit faster than what I just wrote out, right? Okay, but what did I do? I said PV equals nRT. When is PV equals nRT true? Not quite always. When is PV equal nRT true? With gases. Okay. When is your expression 22.4 liters is 1 mole true? Gases at STP. Okay. So I just solved for the fully correct one, gases. Okay. But my answer should come out to your answer, right? Because if it doesn't, I screwed up. Or you screwed up. Okay. So can someone do a calculation for me? 0.0821 times 273.
22.413.
Those of you who didn't hear that, that little calculation that I got written down there becomes 22.4. Anybody notice anything interesting? That is exactly what you solved for. Why is my way better? And massive air quotes for those of you at home. Why is my way better?
Okay, it says it's not STP.
If it's not at STP, I'm right. Right? My way will allow me to substitute those temperatures in, those pressures in, to get the correct answer. The other way will now be invalid because we wouldn't be at STP, which means when we solve the mathematics, it doesn't equal 22.4. Okay? So that 22.4 thing that they're telling you to memorize in Chapter 8 literally comes from the expression talked about 2 chapters later. Right? So they're saying, here, memorize this thing. Don't worry about where it comes from. This is where it comes from. It's coming from the ideal gas law.
So then, now on a test,
Okay?
when you said that it's impossible to solve, it's now not impossible.
It's now not impossible to solve, but part of that information still needs to be included. If I don't say at STP, what do I have to tell you?
The temperature and pressure.
I still have to tell you the temperature and the pressure. Okay? Then it's not impossible to solve. If I don't tell you temperature and pressure, it's still impossible to solve. Okay? So we'll pick up there
So where?
Tuesday?